Hello everybody. In this video we're moving on to chapter 4, and this is exciting because in chapter 4 we get to talk about a new category of calculus called integral calculus. Everything that we've talked about up to this point has been what's called differential calculus, meaning it's all about derivatives. But now we're going to move to integral calculus, which is all about integrals. And in order to understand integrals, we have to first understand this process called antidifferentiation. Differentiation is the process of taking derivatives. So antidifferentiation is the exact opposite. And what I mean by opposite, what I really mean is the opposite direction. It's kind of like taking a derivative backwards. So what do I mean by that? Let's go into a more mathematical definition. So we consider a function capital F of x an antiderivative of lowercase of f if, when you take the derivative of capital F, you get lowercase f. In other words, if you have a function lowercase f, and you're wondering, hey, what's the antiderivative of this? You're looking for the function that if you took the derivative of it, you would end up with lowercase f. So that's what an antiderivative is. And our notation for this is a really skinny s. And so we'd say, if we take the antiderivative of lowercase f, and also part of that notation is this dx, so this is part of the notation as well as the skinny s, then we get that antiderivative. So let's look at a quick little example here, just to help it make sense a little bit more. Let's consider the very simple function of just x. What would its antiderivative be? Well, the derivative of x is 1, but that's not the direction I'm going. I'm going the opposite direction. What function will give me a derivative of x? And that function is actually 1/2 x squared. Why? Because try taking the derivative of this. If I take the derivative of this, I'm going to use the power rule. That 2 comes down and I multiply it with the 1/2, giving me 1. And then I subtract 1 from that exponent. X to the 2 minus 1 is just x to the first. And 1x to the first is just x, which is the function that I started with. So that's what it means to be an antiderivative. What function, when you take the derivative of it, will give you your starting function. But something to keep in mind here is this is actually not the only antiderivative of x. I can come up with a different antiderivative very easily. All I have to do is add a number at the end, specifically a constant. This still counts as an antiderivative because what happens when I take the derivative of this function now? So if I add a plus 3 to it, what happens when I take the derivative? The derivative of 1/2 x squared still ends up being x, and then the derivative of 3 ends up being 0, leaving me with still just x. So it turns out when you find an antiderivative, there's actually an infinite number of possibilities because you can add whatever constant you like and it still counts, it still works. So to notate that, we actually add a plus c with our integration. This plus c is known as the constant of integration. And it always shows up whenever we're finding an antiderivative because any antiderivative, you can add a constant to it and it still works. It still works. And so we show that by this plus c that we put at the end. Okay, so let's look at some basic antiderivative rules. We have lots of derivative rules. So let's see if we can come up with some good antiderivative rules since the process is very similar. It's just the opposite direction. Well, let's start out with a nice easy one. What's my antiderivative of e to the x? Well, what's going to help me think through this is to think about, okay, what's the derivative of e to the x? The derivative of e to the x is just itself. So if I wanted to go backwards, what happens? You still end up with the same thing. So you get e to the x. But remember, you can add whatever constant you want to it, and it still works as your antiderivative. Let's look at another one. What's the antiderivative of a constant? Say you have a constant function, like the antiderivative of just 4. What type of function will give you a derivative that's just a constant? Well, that's linear functions. So I can just have a linear function where my slope is that k. So kx. And because any linear function would work, I can add a plus c. What about a power function? What if you have x to the p power? Well, we saw an example of this earlier where I was just working with x to the first, and it turns out I can come up with a nice formula for these type as well. It turns out you just get 1 over p plus 1 x to the p plus 1. And then I'll add the plus c. So that's my antiderivative rule for power functions. Notice how it's similar to my derivative rule. It's just kind of the opposite. Instead of subtracting from the exponent, I add to the exponent. Instead of multiplying by what my exponent value was, I'm dividing by what the exponent value now is. But there's something to keep in mind, though, with this power rule. It works for everything except for having an exponent of -1. Why not? Because if I tried to use it for this, if I tried to use the power rule, I'd end up with 1 over 0 here. And of course, that's an undefined value. That's a no-no in math. So let's look at that case specifically. What would the antiderivative of x to the -1 be? Well, if we think about negative exponents, this just means you have 1 over x to the first, or 1 over x. Well, hopefully this looks familiar. We've seen 1 over x before, where it's the derivative of natural log of x. So if I'm asking myself the question, what function will give me a derivative of 1 over x, the answer is natural log of x. So for this special case, where p is -1, we actually get the antiderivative of natural log of x. Well, since we're talking about logarithms, let's do another exponential one. What if I have e to a constant times x? Normally, what would my derivative rule be? My derivative rule would be to multiply by that constant and then keep everything else the same. So we're going to do the opposite. I'm going to divide by that constant and keep everything else the same. Well, now let's look at some of the smaller rules. For example, what happens if I want to take the antiderivative of a function that's being multiplied by a constant? How does this constant affect your derivative? Remember, it really doesn't. The constant multiple property of derivatives says you can just ignore that c and then multiply it on at the end. It doesn't affect your derivative. So, for that same reason, it doesn't affect your antiderivative. You could ignore that constant and just take the antiderivative of your function and then multiply by the constant when you're done. The same thing is true for if you're adding or subtracting functions. How does addition affect derivatives? It doesn't. You can just take the derivatives separately. And so for that reason, the same is true for antiderivatives. I can just take the antiderivatives of each function separately and then add or subtract them together. What if I have two functions multiplied by each other? Does that complicate your derivative? It does, which means it's going to really complicate your antiderivative. So we don't have a nice simple rule for if you have functions multiplied together. Or if I have composite functions, functions inside of functions. That complicates your derivative, so I don't have a nice antiderivative rule for that. But these are the antiderivative rules you guys are going to be using. Okay, next let's look at a context where antiderivatives actually make sense. So recall in previous sections, if we have an object in motion, we like to use S to represent the position of the object, where t is your time unit. If I were to take the derivative of this function, what does it tell me? Remember, it tells me velocity because it's telling you how the position is changing, the rate of change of position. Okay, what if I take the derivative again? The second derivative. Well, this gives me the acceleration because it's how the velocity is changing. Is the object speeding up? Is its velocity getting faster? Or is its velocity getting slower? Is it slowing down? So of course, that's moving in this direction, right? Taking derivatives is moving in that direction where you're going from position to velocity to acceleration. That's taking the derivatives. Remember though, an antiderivative is just moving the opposite direction. So antiderivatives would be moving this direction. Therefore, if I were to take the antiderivative of my acceleration function, notice how I'm using dt now because my independent variable is t. What's my antiderivative? I get the velocity. I still would put a plus c though because I can still put whatever constant I want there and it would still count. And then if I take the derivative of the velocity, I get the position function because I'm moving in the opposite direction. So this concept is a great example of how an antiderivative is just the opposite of a derivative. Now this seems pretty silly though, that I can just put whatever plus c I want, I can put whatever constant I want, and it still counts when we're working with an actual context. And the reason why this maybe doesn't make sense is because a lot of times with a context like this, with an actual situation, we're given various data points. So it actually is possible in certain situations, and we'll look at an example like this in the homework, where you can actually solve for what that arbitrary constant is. So something to keep in mind is if you are given a data point, in addition to the function, right, in addition to whatever function you're working with, if you are given a data point, then you can solve for the constant of integration. Meaning it's not just an arbitrary constant anymore, it has to be a specific constant that goes there, okay? So a lot of times this data point, though, just is your starting point, and so that would also count. If it gives you a place to start, then that counts as your constant of integration. And once again, I'll go through an example of that when we go through the examples video. Okay, but that's the concept of antidifferentiation. Go ahead and try some homework problems, and then if you have questions, take a look at the examples video. Good luck, guys.